everybody. Welcome to Border City Data. This month we are taking a look at Ontario water quality data. But before I dig into that, I just want to make a little bit of a pitch about Hackforge. Windsor Hackforge is the organization that sponsors these events and supports us and the other interest groups that are part of Hackforge. It is a registered nonprofit. It's been around in Windsor for over 10 years, and it is driven by volunteers like me. So I just wanted to make a pitch. hackf.org is the website. If you are interested in being an active part of our community, then you are more than welcome to check out the site. Get in contact with our managing director, Lauren, who is a wonderful resource, or Matthias, our volunteer coordinator. Either one of them can direct you to the right place. Okay, my spiel is done, but I do recommend that you do that. Okay, with all the preambles aside, what is the data available on water quality in Ontario? For streams and rivers, we can look at the data provided by the Provincial Water Quality Monitoring Network. And that is essentially a network of conservation authorities in Ontario who take samples. I think some of these are on a monthly basis. Some of them seem like they're more annual. There are different frequencies, but each of these conservation authorities attends their share of the 400 sites across Ontario where water quality monitoring is done. And they take samples and they evaluate those samples to understand things about the composition of the water. This data goes back to 1964, so there is a rich data set for you to dig into. And there, as it says on the slide, there are 59 individual measures that are reported by this data program. And that includes things like lead levels, mercury levels, nitrogen levels, oxygen levels in the water, all the stuff that you want to know to understand the health of a waterway. So how do we access this data? Well, first of all, let's take a look at what this data looks like. We can get it in a number of different formats: Excel format, JSON, or XML. The API emits JSON. And I just pasted a little bit of the output from the Ontario Open Data Portal so that you can take a look at what kind of fields are available and what kind of data is available here. So we can see that there is the analyte. The analyte, what a wonderful word that is. That is the analysis being performed, the date and time it was collected, the identity of the lab worker who took the sample. There's some stuff there for tracking the sample result, the units that you should use to represent that result, and any comments on the result, as well as the methodology used. So one thing that you might note is that there are, rather than spelling out the collection site details and the methodology details, those are presented to you by identifiers. You can actually reach the Ontario Open Data API to get the details on method and the details on collection sites. So in this particular example, we are collecting the data on the sites as well, because those identifying numbers don't mean a whole lot, and we do want to visualize this data. And one of the things that people will want to know when they're taking a look at a chart is, what stream or rivers information am I looking at? So that's what the data looks like, and we get access to it through the Ontario Open Data Portal. Some vital statistics on the portal up here on the screen, the URL and the platform it uses the CCAN platform, which is a pretty common platform used for open data portals. And that means that it exposes data using the CCAN API. And there on this slide is also a link to the documentation. But within the API, within the Open Data Portal, there is also documentation that is readily available to you. You can actually click on it and even see sample API calls for the data set that you're interested in. It's very nice, very comprehensive. And the The screenshot indicates there are almost 2,900 data sets available on Ontario's data portal. And the cool thing is that once you learn how to use the API, you use the same tooling to access any of those data sets. The script that we're going to work with today, I built it to be a little bit modular, so that if you want to use this tool to look at some other Ontario data set, you need to make minimal changes to one file in particular in order to do that. So today we're talking about water quality, but we could be looking at almost anything presented on the Ontario Open Data Portal, and we would be using the same tooling. So to use the API, there's the base URL on the slide. It is data.ontario.ca is the domain name. And the endpoint for the API call is also listed on the slide, as well as a couple of parameters. So this is all pretty typical stuff if you have experience working with an API to get data. These are the kind of the required parameters that you would have. You need to identify what data set that you want to access. You may have noticed that is some kind of a hash value. You can see a sample down here. Not particularly user-friendly, but it does do the job. You also need to identify how many records you want, okay? And the number of records that you want to skip. So by doing that, by using those two parameters, you can page through the API and deal with one page worth of data at a time. And that's really nice for large data sets because it means that you don't have to request the whole data set at once. You can request it in chunks. So if you're collecting a large amount of data, that is a helpful thing to keep in mind. For the record, I did pull this entire data set in with one query and it worked just fine, roughly 130,000 records. So it wasn't a problem, but that paging capability is there for you. And this is what the API output looks like. So this particular result is actually from the station data. This is not a water quality sample, but the essential features are the same. And what we're really interested in is the data in the result key, and then within the result key, the data in the records key. And what you'll get there is an array of records, okay? And you can see the columns and values provided there in the records output, along with some essential links, including the link to the next chunk. So you can programmatically use the links component of this JSON in order to page through the record set. So that's what the output looks like. That's what we'll be working with. So the solution that I built here, it is a Python script. We're using 3 modules that we need to import. If you haven't used Python before, modules are reusable components of code that are either written by you or written by a third party. In the case of third-party applications, they are versioned and stored in a repository that you can access using the tool called pip. Okay, so in this particular script, we're using the requests module. Requests is the module that we use to make requests to web servers. So we'll be using that to actually communicate with the data portal. Petal is a module that's used for ETL, extract, transform, and load projects or work on data sets. And I really like Petal. A lot of people prefer to use pandas, and pandas is okay. I'm not denigrating pandas in any way. Petal is the tool that I prefer to use primarily because Petal is designed to be part of an ETL pipeline. So its memory consumption is more appropriate for working with large data sets in an automated way. Pandas is great for data visualization, exploring data sets. I just want to point out the reason why I choose Petal for most of my projects like this. And you'll get a chance to look at the capabilities of Petal in a couple of minutes. And finally, to make the charts, to visualize this data, we'll use matplotlib, which is pretty much what it says on the tin. It is a library for making plots, okay, charts, and that's what we'll use it for. And our solution has a couple of components that I want to dig into individually. So there's a little list there. There is the Python script itself and the associated modules. There's also something called a Docker file. And the Docker file is used to provide the instructions to Docker to create for us an image which gets converted into a container. And that container is something similar in concept to a virtual machine, but they're much lighter weight than virtual machines. Containers are relying on the underlying operating system that your computer is using, but they do provide isolation for processes. And for our purposes, you can isolate an application environment in development. You do not need to install all of the required software in order to do your development work on your local computer. And what's really nice about that is if you do a lot of development work, what you'll find is over time, you will have conflict problems where you need to have multiple versions of some piece of software installed in order to do the work. And you have to, in order to do work on different projects, and you have to manage all that confusion on your own local machine. You don't have to churn libraries and module installations on your computer. Essentially, it helps you keep your computer a little bit cleaner, your own local development machine a little bit cleaner, and have a development environment that is customized specifically to the task at hand. There are a whole lot of other ways that you can use Docker in production, but I'm focusing on development. And I'll be honest, I'm a Docker newbie. This is a product that I've only started to dig into and learn. So if I misspeak and you're a Docker expert, maybe you let me know in the chat. So as I said, the Docker file contains instructions for building the image that will be used to develop or to construct the container. And in this case, I just have a few commands in my Docker file. I'm specifying the base image that I'm going to use, which is an official Python image. Okay, I'm specifying my working directory. And then when we build this image, we copy the requirements.txt file from the development folder into the app folder on the remote computer. Then we run pip to install all of the modules that are specified in requirements.txt. And then we copy the rest of the source code into the target image. And once all that is done, then the container can be started and it is ready for development. Okay, so not a whole lot to say about the requirements.txt. Essentially, it's a lot nicer than manually installing the modules that you need. And if you intend to create code that's portable, perhaps work on a team with other developers, and you don't want to constantly be communicating about the details of what needs to be installed and when, then using a tool like this is very helpful. Okay, and we have 3 files that we're going to be looking at tonight. The main script is get PWQMN data, okay? And what that script is concerned with is loading our modules and handling the Petal processes. So that script only really handles the data transformation itself. And the reason that I isolated the data transformations into that script and moved all of the other functionality elsewhere is for reusability. In ETL work, the transformations that you do are often very specific to the data set that you're working with. And there's not a lot of portability there in general. And when we look at the source code, you'll see what some of those specific transformations that have to happen on this particular data set, and in fact, this particular subset of the data that are unique to it. And you'll perhaps start to see why it's not the best idea to mix your transformation code with your other code. Okay, and the modules that I created, the two modules, each of them contains one function that is used by the main script. Okay, and the Ontario API script handles all the interaction with the API itself, and the BCD chart script generates the line charts for us. And I would say both of these modules are in their infancy. This is an approach that I tend to take to software development. For small projects like this, I will start with a purely linear script. Start at the step 1 and just kind of script everything right down to step 100. Then once I have it running and have proved that I can do the task, then I start refining and refactoring. So the first refactoring was looking at what code might be reusable here and moving it out into modules, and at least doing a little bit of thinking about how I might want to build out those modules in the future. So for example, BCD chart generates one kind of chart. It generates a line chart. Okay, it is expecting a set of data. It's expecting to be provided 2 arrays of data, and one of those arrays is always dates. So it's very purpose built for building a very specific kind of chart, which happens to be exactly the chart we need. No point in doing any further refinement than that for the purpose of building this particular script. But on the next project that I work on that has a charting component, I already have a function library started. And my view of sort of small casual projects like this is that it's not a good idea to impose an architecture on your solution before you really understand the ways that you're going to use it. And so I'm not imposing any future concerns onto my functions. Okay, I'm just kind of getting them separated, using them for the purpose that I have in this script, and the next time that I need them, that kind of proves to me that there's something here, there's some value here that I'm going to keep coming back to, and then I will continue to refine as needed. So that's kind of the way that I approach little toy small projects, something that is, one developer is going to work on for 1 or 2 days or less. That would be kind of the scope that I would consider for taking this kind of a casual approach. Okay, now the fun part. I'm going to do a little bit of a demo. So I'm going to sit down at my laptop, and apologies to the folks who are remote because you are getting an extreme close-up. Okay, so I actually want to start with the module that handles the API calls, because I think that's where most of the value is for folks who are here today for Border City Data. So I want to make sure that we get as much of that done as we can. Okay, so at the top of our script, we import the 2 modules that we're going to need. We need the request module, which we did need to install, and we also need the built-in JSON module. There are some modules built into Python that are shipped with the distribution of Python itself. JSON would be one of those modules. And here is the function that gets data from the Ontario API. So essentially what we're doing here is we are creating a function. It has 2 parameters. The resource ID, which is that hash that represents the unique identifier for this particular data set. And the other parameter is the limit, and that is the number of records we're going to retrieve in each request. So now you can see the code that I was talking about. I think I was sitting on the parameters of the function. So the second parameter is the number of records that we want to retrieve at one time, and the resource ID parameter is the hash that identifies the specific data set. So then in this function, we initialize a couple of variables into their default positions, and then I set a flag true, and then I use that flag to control essentially the loop here. And so while we're in the loop, we request data from the URL specified. Okay, we load that data into JSON, and as long as it's not empty, we leave the flag true. Okay, so we'll continue the loop. If there are no records in the area of the JSON that is reserved for records, if that's an empty array, then we know that we're at the end of our request and we can stop requesting more data. If not, then we need to append the data we just retrieved to our big pile of data, and then increment our offset value by the limit. So if we're requesting 100 at a time and our initial offset is 0, then our second offset would be 100, the next offset would be 200, and so on and so forth. And finally, when all is done and we have all the chunks of data, I call a little utility function to flatten that list, because what happens is we end up appending to our data set, each of those segments of the data as its own array. And so I just flatten that out. There may be a cleaner way to do this, but I did write this script pretty fast. I flatten that list out into a single array so that all of the records are in one place. That's it. That's all. That function handles getting all of our data. Once we've got our data, so now let's take a look at our main script, and you can see the imports here. We're grabbing Petal, the data manipulation library for ETL that I mentioned earlier. And then we're also importing the two modules files that we have in this particular development folder, BCD chart and Ontario API, to get access to those functions that we're using. So we're using a limit of 10,000 records, very aggressive. Then we make two calls to get Ontario data, and in each of those calls, in the first call, we're getting the information about stations. If you remember the slide that had the station data on it, that's the record set that we're getting. What we're really interested there in is the name of the station. But I want to add that if you're interested in making a digital map of this data, and I think it would be a really interesting project to do. If you're interested in making a digital map, you'll want the station table because it contains the latitude and longitude of that particular station. So if you don't include the station table data, or the station data rather, if you don't include that, then you're not going to be able to geographically locate your stations or identify them by name in your output. So for that reason, we get the station data. On line 12, we get the specific observations from the API for specific stations on specific dates. Okay. Once we get all that data, in each case, we load it into a Petal table. Okay. So in this case, we are loading a Petal table from dictionaries. So you'll see that call on line 9 and again on line 12 to the Petal module. And we are using the specifically from dics to get dictionary data into a Petal table. And the reason that we want to get that data into a Petal table is so that we can use all of the wonderful data transformation and manipulation tools that Petal gives us. You can find full documentation for Petal at the website petal.io. It is a fantastic resource, tons of documentation, lots to learn. So the first thing that we need to do is take these two tables and join them. Those of you who are familiar with relational databases will be familiar with joining tables in a query. Essentially, what we're doing is we're taking two sets of data and we are connecting them with a piece of information that both sets of data have in common. In this case, it's the station identifier, okay? In the case of our two tables, we'll now call them the observation table and the station table. In the case of our two tables, we have the information that we're interested in using to connect those two tables is stored in different columns, okay? In columns with different names. Petal has a facility for this, and it allows us to specify the left key and the right key, okay? So the key in the table on the left and the key in the table on the right. So using collection site in the observations table and station in the station table, we can merge those data sets. So there are many, many, many more rows of data in the observation table than the station table. The station table has a list of all the stations in Ontario, but the observation table contains all of the observations at those stations over the course of a year, a 5-year period, a 10-year period, whatever it might be. So in that case, what happens is the join looks to the station table and sees many instances of a matching identifier in the observations table. So what we would call this in relational database terms is a one-to-many relationship, okay? There are many observations for one station, and each station is listed once and only once in the station table. Okay, so what I specifically want to do today is create a chart for every station in Ontario for 2021 showing the lead level throughout the year. So we are going to filter our table so that we're only looking at the data we're interested in. In this case, this happens on line 18. We're only interested in lead, okay? I only want to know, for the purpose of this work, what is the lead content in that water? So we use Petal Select, okay, that allows us to select a subset of our data, and then we can supply an anonymous function that tells us how to evaluate each record. So in this case, the filter conditions are that the record identified here with the parameter rec, that the record in the analyte column contains lead, equals lead, always and only equals lead. So all of the other records get filtered out. We get a table back called the lead table with both observation and station data for any observation involving lead, okay? Then we generate a chart. So starting on line 21, we loop through all of the stations in the data set, and we grab the name and the station ID, okay? We grab both of those pieces of information for each record in the loop, and then we build a table of the specific records relating to lead from the lead table for that individual station. So we do another filter on our lead table here to get only the specific records for that station. Then I was messing around with things, and I wanted to make sure that we didn't end up with a record that had a collection, 2 instances of the same collection date at different times with the times in the wrong order. So we have a single field for collection date, a single field for collection time. I add a field. I use Petal on line 27. We use Petal to add a field that contains a computed column. And that computed column is again identified with an anonymous function, okay? And in this case, what we're doing is we are creating a new record a new field called D. Okay, that column goes into our table and it's called D. And it is the concatenation of the date and time with a space in between. Okay, so that's a really powerful feature of Petal. You can not only extract, filter, and report data, but you can also synthesize new data from what you've got. Okay, then we sort the table by that date and time field, that combined date and time field that we built. And then in the case of on line 33, here's an example of the kind of stuff that you have to do in ETL to solve a specific problem that makes this stuff less than portable. In this particular case, the way that the lead analysis is performed, and in order to prepare for tonight, I learned way more than I ever thought I would or would want to about lead testing procedures. And essentially, from what I can glean, this testing is performed in a way that only allows a certain amount of precision. So the results are always provided as less than X. The amount of lead in the water is less than some number. So the lowest number is 7. Less than 7 is one result that you'll see a lot in the output. And so the problem with that is that in our charting library doesn't like that less than symbol reported before every result, because then it treats those results, those values, as a character string instead of treating it as a number. And that fouls up all kinds of stuff in the charting library, because we end up with the range of values of our data reported in alphabetical order instead of being reported in numeric order. So in the case of 2-digit numbers or 3-digit numbers, it gets sorted based on the initial digit of that number, and it doesn't work. So I have to specifically convert, do a transformation on a specific column in the station table. Remember, this is our tiny table that contains only the output for this particular station that we're working with. And we do a conversion, okay, on line 33. And what we're doing here is we are again running an anonymous function against our the content of the result column, and we're just checking if that first character is a less than sign, get rid of it. If the first character in that result is a less than sign, let's strip it out, okay, and then we're going to return the integer version of everything that's left, okay? So that's the transformation we do there. So that concludes all the transformations that we have to do. We now have a table that has the content and the shape and the size that we want to generate our chart. So there's nothing left to do except call our, go ahead.
Question in the chat, how does it remove the less than sign?
Okay, so thank you for asking that question. So let me get into a little bit more detail here. So one of the parameters that we provide to petal.convert, okay, is this little construction here called a lambda function. And essentially what we're doing is we're providing an anonymous function that is going to be executed against every row. Okay, so we use the identifier V to represent the value, okay, the value stored in the result column in that particular record. And so then using V, we manipulate V, okay, we manipulate V, and the result of that manipulation ends up being the value that is placed into that particular row of that particular column. So that little bit of code there is how we do that work. So once we've got all that done and we've got the data we want, we're ready to visualize it. So we call out to our charting function, okay, And I'll just show you what that function call looks like, and then we'll dive over to look at that code. And then finally, once we're done doing that, we'll actually run this and generate some charts, and you can see what they look like. Okay, so what we supply to the generate function is the table itself, okay? The values in the table itself for collection date. Now, what happens when you ask Petal for the values in a column is that you get back an array, okay? So we're asking Petal to give us two arrays here and supply them as parameters to our function. The array of collection dates and the array of results, okay? And then we provide some information to the library about how we would like to decorate that chart, what we would like to be the label for the y-axis, what we would like the name of the chart to be, which is going to be the station's name, and what we would like the name of the output file to be, which is going to be the station identifier. So why would you do that? Why would you output a file with the station identifier as a name instead of the station name? And the reason that I did that is I'm imagining a use case for this output. I'm imagining a use case. So we might be populating a dashboard for each particular waterway in Ontario. And if we were creating a dashboard for each waterway, we would want those files to be named with something that we could use very reliably to identify that location, that specific location. So we use the station identifier because we know it will be unique, okay? We don't know that every station name is unique. There's Turkey Creek is one of the waterways that you're likely to see tonight in our demo. There might be 2 Turkey Creeks in Ontario. I don't know. So in order to protect ourselves against that risk, we use the name of the station for display to humans, and we use the station's identifier anywhere where the only entity that's going to interact with it is a computer. And that is the entire script. Essentially, then we also dump the data out to a CSV, and that's just so that we can take a look at it. That's really debugging code, just so that we can take a look at what the lead table itself looks like. Okay, and finally, the charting. So we are using Matplotlib. Matplotlib is our charting tool, and specifically we are using 2 components, 2 subsets of those libraries. We're using PyPlot and dates. Okay, so our import statement is specific. It's specific to the subset of the functionality of this library that we want. Okay. So then here's the generate function definition. You'll remember what it looked like when it was being called, okay, when it was actually being called in code. And there are all the parameters that we talked about. And we do some simple things like set the font size for the output, do a little bit of configuration of the chart. So we've got to set some subcomponents up. The subcomponents that we're setting up are specifically the figure itself, okay, the actual plot itself, and then the axes. So that's what we then are manipulating to identify specifically where we want to see tick marks on the x-axis and what the labels are going to be for the x and y axes of our plot. And once we've got that, we set the title. Okay, we plot the chart with the 2 arrays. You remember those 2 arrays we created with Petal, the dimensions, which is our dates, and the values, which is our result values for that specific date. Okay, we put a grid on top of that graph so that we have a nice set of grid lines that we can use to help identify what any specific point's value is, and then we save off the entire figure to a file, and we close it. Very important to remember that last bit. That was a bit that I neglected to include before my first run, and Python was quick to inform me that I was generating hundreds and hundreds of unclosed plots. So always important to clean up after yourself and close your plots. So that's the entirety of the solution, and I'm now going to execute it. So while we're executing it, why don't I take this out, and instead what we're going to do is we are going to actually show the station table when it's ready. So we'll be able to watch that. Okay, there we go, right there. Great. Okay. There we go. So we'll be able to see in our output window, we'll be able to see the station table when we get to that point for each of the stations. All right, now I've got to move my little Zoom control panel here so that I can get at. There we go. Okay, so now we're going to execute the code. It doesn't do a whole lot interactively, except it will print that station table when it gets there. So we can take a look at that. Okay, and what we'll see is our folder will start to fill up with, there we go, there's the first one. It will start to fill up with images. So let's take a look at what pedal tables look like in print view. So here you go, here's all of your columns along the top, and there's all the data underneath, and you'll see a few rows of data there. Okay, our first record, super fun. Our first record is local to us here in Windsor, Essex. There's Turkey Creek. Okay. And what you can see, this data comes from 2021. Each of the previous decades back to 1970 is stored in a separate section of the API. You actually have to call each of them separately. And then the data from 1964 to 1970 is in its own section. You see those charts being generated. This is what they all look like. We've got the name of the station across the top. The x-axes are labeled. We've got the lead concentration in, I believe that is milligrams per liter. And it looks like Turkey Creek had pretty high levels of lead, over 20 milligrams per liter in the first couple of months of the year. In this case, in months 4, 5, and 6, and then the lead levels went back down to 7, which we know is less than 7, which means that that's as low as the apparatus used to investigate these waterways goes. So that's what that looks like. I'll just scroll through a couple more of these. Here's River Canard.
Another question.
Yeah.
How do we run the file?
Okay, so in my case, I'm using Visual Studio Code. Okay, so in my case, I'm using my editor to interact with the application and actually execute the script. But if we were going to do it from the command line, man, you folks are going to make me figure out where my GitHub folder is. There we go. Can we just open a, yeah, so nice. Thank you, Windows. Okay. There we go. Okay. All right, here's our data. So if we were going to execute this from the command line, we would just do it like that. Okay. We would call the Python interpreter from the command line and supply as an argument to the Python interpreter, we would supply the name of the file we want to execute and the path to it, and this would work. So let me stop this execution that's happening up here. Okay. Here we go. I believe I've got it stopped. There we go. stopped it with keyboard interrupt. Okay, so that's ended there. And wrong place. Here we go. And now I can execute it over here, and it'll do the same thing. So what you'll see here is the output will eventually start to happen. You'll start to see the sample of the lead table, sorry, the station table. You'll start to see that sample. There we go. That means that it's processed that particular station, and on we go to the next one. So there are some things that if you knew that you were going to run this script interactively a lot, there are some things that you would do, like include a little bit more output at the terminal so that the user who is executing the script can see perhaps the progress, how many stations total and how many stations have been processed. Nice little things like that. But for the purpose of this demonstration, we didn't do any of that fancy stuff. And that's there you go. That is the code. So we've got a couple more minutes. First, I'm going to ask if anybody has any questions or if there's anything that you folks would like me to dig deeper into. The disembodied voice you hear, by the way, is Jessica Sartori, who's being kind enough to read through the comments and manage the Zoom for me. Okay, seeing no questions. Nothing? Okay, great. Then what I'll do is, with a little bit of trepidation, I'm going to talk to you in a little bit more detail. Oh,
Derek says still can't run it.
Still can't run it, Derek. Okay. So I'm not sure if you are not using Docker, then you may need to right. You may need to, and I see Sharad. Sharad is always on the case, and he's in the comments helping out. Thank you, Sharad. You need to have Python installed, and you need the requirement modules. You need those installed. So the nice thing about using Docker is that we can create a development environment with all of our requirements there for us. So if you grab the repository, then you can use the Docker file to generate a Docker image. Or if you've got Python installed, you can install those modules. Either, I believe it would look like this. And I've got a Python expert in the room, so he's going to nod his head if I've got this right. Hey, thumbs up. Okay. So if you run pip like that, it will look through requirements, the requirements.txt, and because I'm on Windows, it's going to give me some yellow scare quotes.
No, it's just saying pip 7
Oh, okay. All right, that's fine. So yeah, so what pip identified for me is that all the requirements identified in requirements.txt are already satisfied. If that wasn't true, it would install all the required software for me. So those are probably the steps that you have to take to get it running on your machine. And if you're struggling, and I know, Derek, you were planning on coming in tonight, but you're a little under the weather, next time you're at a HackForge event, pull me aside. I'll have this stuff on my laptop, and we can work on it together. Okay, any other questions? All right, folks. Well, then I am going to give you guys 10 minutes of your evening back. I very much appreciate your time and attention. Again, hackf.org is the place to go if you are interested in doing what I'm doing now or volunteering in some other way with HackForge. We would love to have you. And you can always find me if you're interested in asking some questions, if you've got a follow-up question or you'd like to make a suggestion about a future Border City data, you can always find me. I am D. Sartori on Mastodon, or you can email me, doug@sartori.ca. And we're not going to type that anywhere just in case spam bots pick it up, but doug@sartori.ca is my email address. Feel free to drop me a line anytime. And thank you very much, everybody, for attending tonight. Have a great night.